which is about the 3D camera. Then let's go to the lecture 4, and it's lecture 5. It should be lecture 5 because in this semester we have 5 lectures about the sensors. So this lecture is mainly about the time-of-flight sensors. It's about time-of-flight sensors. So the typical time-of-flight sensors are sonar sensors, ultrasound sensors, Lidar sensors, and radar sensors. I'm not going to talk too much about radar sensors because we're not using that much. The radar sensors is on the bottom right picture, so we are not using that too much. It's always used in the military and also about forecasting the weather. So we will introduce sonar sensors, ultrasound sensors, and Lidar sensors. All right, so for the sonar sensors, the full name of sonar is sound navigation and ranging. And it uses the reflected sound waves to detect, locate, and determine the speed of the objects. Which means it uses the sound. It uses the sound to detect and locate the object. Right, so that's the sonar, and sonar is always used in the underwater environment, because in the underwater environment, the optical sensors, they may not be used, and they use sonar sensors a lot. And here is a YouTube video about an example of the sorry, there's an ad. There's a YouTube video about the YouTube video about the sonar used in the underwater environment. Let me know you can't see the video. Okay, so maybe there's some issues about sharing the sound, but this is the case. I can hear the sound. Sorry about that. So there's a link on the slide. So if you are interested, you can watch the YouTube video yourself. And they use some kind of like multi-beam sonar to detect the sea base, As if, okay, so that's an let me stop it. So that's an example about the use of sonar in the underwater environment. So I I did a very huge project about the seabed mapping when I did my PhD in Peking University, and I used the multi-beam sonar. That's the only sensor we can use because we are not getting a submarine to make it quite close, to make the sensor quite close to the sea base. If it's quite close to the sea base, then you can use camera. Otherwise, if it's far away from sea base, you can't see that. It's too dark, you can't see that. Then the sonar is the best thing we can use. We use a multi-beam sonar, as similar as what they have is a multi-beam sonar as a line. And then when the boat move forward, it's some kind of like brushing, and then you can reconstruct the seabed structure, of the spec structure from the multi-beam sonar. All right, so that is the sonar, and the sonar is the idea of the sonar. So most of the sensors idea is originally from from human self or from the animals. So some animals, for example, I think all of you know it, right? Like bass or dolphins, they have this kind of like similar principle as well. So they generate some kind of like sound, and they detect the echo and to know the object, right? So bass use that and dolphin use that as well. And the first of use, so on the record, the first of use of this kind of sound in the water is by Da Vinci, and he put a tube in the water, and listen from the tube to listen to the sounds to detect the vessels. And this is the first recorded use of sound in water. And the sonar was patented in 1913. So 1913, so it's not that long. And then it's really well developed, really well developed in the World War, in the Second World War, because the submarine they developed a lot during that time as well. All right, so for the sonars, there are mainly two types of sonars. It's like two types of sensors as well. The first one is active sonar. This is what we really always used, is the active sonar. Active sonar means it generates the sound and hear the sound by the generated, right? So that's the active. The generated sound and listen to the echo by the generated sound, right? And in the active sonar, we also have three modes. So one mode, we call it monostatic mode. So which means the transmitter is the one to generate the sound, and the receiver is receiving the echo, receiving the sound back. So the transmitter and the receiver are at the same place. So that is the monostatic mode. And there's another one called bistatic mode. So which means bistatic mode means the bistatic mode means the transmitter and the receiver are replacing by different locations with a distance, and then it generates the sound, which means there are multiple transmitters and receivers. So as I mentioned, the multi-beam sonar is one of the case. I used the one with 64 beams, and there are 16 and 32 beams as well. So multi-beam, because the sonar only have one direction of detection. So if you have multi-beams, it's like it can scan a line, and with the move, they scan a plane, right? So that's a multi-static mode. And for the passive sonar, it always used to detect some objects which can generate sound. For example, in the Second World War, they used a lot of passive sonar to detect submarines. Right. So if you have a submarine, your engine will definitely generate some kind of sound, and then that sound will be heard by the passive sonar. And they have a lot of pre-calculated, pre-saved model, and to getting that sound with the energy of the sound, and then also the some properties of the sound, and they can calculate and they can predict what kind of like object it is, and what's the distance between that object to me, something like that. So the passive sonar is not that commonly used, not commonly used by us, but it's definitely used to detect the submarines. All right, so the principle of sonar is quite simple. I think I mentioned that before. It's just they use transmitter to generate a short burst of sound. It's generate a ping and listen to the echo. And because you know the time difference and you know the speed of the sound in the water or in the air, then you can calculate the distance based on the speed of the sound and also the difference of the sound, the difference of the time, right? So that this is what we call time-of-flight sensors. That's time-of-flight sensors, right? And this is the principle of the sonar. The principle is quite simple. And there are some issues or some models about the uncertainties of the sonar. So, for example, the sonar can provide an accurate range measurement. So the range measurement is relatively accurate, but the angular resolution is not very good because the sound is not a line, it's not a laser. It has a shape to make it out, right? So that's the sound. So which means the angular resolution is not that accurate. And in some of the cases, the specular reflection will cause the wall disappear. The specular reflection will cause the walls disappear. And also, if you use a sonar in a corner, there will be multiple reflections, and it will cause the error on the distance as well. So those are some kind of like issues of the sonar. So based on that, we know if we have some sonar data, and we can model the uncertainty of that data. And if we want to simulate the sonar data, then we know the model of the error on the sonar data, right? So that is, the sonar will provide accurate range information, but not that accurate angular measurement. So, for example, if you are simulating a sonar data, then you need to provide a relatively small error on the distance, but relatively larger error on the angles. All right, so that's the model of the uncertainty or model of the error of the sonar data. Then that's the ultrasound. As we know, the people can hear, what we call it, the band is acoustic. People can hear from the frequency of 20 hertz to 20k hertz. But the sensors can do much better. And the ultrasound is the sound over 20k hertz, 20,000 hertz. That's the ultrasound. And if you remember, the sonar was patented in 1913, right? It's nearly the same time they got the first ultrasound generator. And in 1928, they used the ultrasound to detect the materials. It is now used. I think most of you may know the ultrasound is used in the medical area, right? In the medical area, but they use a lot of ultrasound to detect materials. When I was at Imperial, so one of my colleagues, he's working on the project with Rolls-Royce. You know Rolls-Royce, right? You know Rolls-Royce about cars, and you know the Rolls-Royce is building the airplane engines as well. So they are working on the airplane engines, and they use the ultrasound to detect if there is a small break or bubble in the materials of the aircraft engine. And this is what they are doing at the moment, even for Rolls-Royce. All right. So the ultrasound is first used in medical in 1942. In 1942, they want to locating the tumor in the brain without opening the brain, right? And in 1950s, they got the 2D grayscale images. We call it B ultrasound or B. It's like B images, right? And in 1965, we can get real-time ultrasound images already. So it developed a lot, and it's mostly commonly used in the in the medical area as an non-invasive method. All right, so that's the ultrasound. And the ultrasound, I think the principle is like similar. The principle is like similar. And for the ultrasound used in the medical area, we always use 2.5 to 14 megahertz as the frequency of the sound. And the principle is similar, but a little bit different. If you remember the sonar, it generates a sound and listen to the echo from the object, right? But ultrasound is a bit different. It can receive the reflected and coming back like energy of the sound. It's not hit one object and coming back. It can get into the soft tissues. So which means it generates ultrasound, and what you received is a continuous changes of the sound energy, the energy. And for different materials, the energy will be different. If you look at the figure here, for different materials, the skin surface is organ. So for different materials, you will get the reflected energy different, right? So that is the difference. So for the ultrasound, for the sonar, it generates a sound, it hit the object, it's coming back, right? So you just get one reflection, but for the ultrasound, it can receive a sequence of the energy changed because of different materials. And that's why it can be used in the non-invasive medical area. All right. So in the ultrasound, the first scan we have is A scan. A scan is just what we mentioned before. So on the x-axis is the depth, and also is the time as well. So time means depth, right? It's the depth or distance. On the y-axis is the intensity, which represents the energy received, the energy of the sound received, ultrasound received, and different energy is presenting the different material of the soft tissue. All right, so that's the A scan. And then later we have B scan. So B scan is the 2D image. If you remember the A scan is some kind of like one beam of B scan. And if we put all the A scan together, you will get the B scan, and which is an ultrasound image. And this is what we are currently used now, right? So you put together, if you remember the A scan, from this A scan, you can find here are the stronger, the larger energy, and here's smaller energy, here's another larger energy, here's smaller energy. Right? If you put them together, and you can see your eye, something like that. Right? So that's the B scan. B scan is putting all the A scans together. And now we have 3D ultrasound already. If you remember, I mentioned something on the heart ultrasound. The heart ultrasound in the second lecture, and then that is the 3D ultrasound as well, and it's putting this kind of like A scans together. All right, and the next one, which is really commonly used, is Lidar, or we call laser, or we call laser scanner, right? So the Lidar, the full name of Lidar is light detection and ranging. And a LiDAR transmits and receives electromagnetic radiations and operate in the ultraviolet, visible, and infrared region of the electromagnetic spectrum. All right, so they use light. They use light instead of sound to detect the distance. All right, so the principle is similar. The principle is similar. They generate a light and receive the reflection of the light and calculate the time difference, right? And they use the time of flight together with the speed of the light to calculate the distance. And the different thing, and the very good thing of LiDAR is because it's light, you don't have to do the multi-beam of the sonar, right? What you need to do is you just need a mirror, rotating mirror inside, and then you can have multiple beams by deflecting the light. And this property makes the angular measurements very, very accurate. So that's why we use laser so much, because it can provide both the accurate distance and angles. That is quite accurate, and that is different from the sonar. And this is why we use it that much in the robotics area. All right. So for the laser or for the LiDAR principle, we use the last pulse measuring technique. Because we are using light, there must be some like dust cloud or something in the air, right? And they may also provide some reflections. But after the light hits the real target, it will not getting any reflections after that. It will reflect it to the receiver, right? So which means you may have a lot of reflections, but we always get the last pulse. We always get the very last one, because after that because it really hits the target, and after it really hits the target, there's no reflections anymore after that, right? So this is what we did. We always use the last pulse measuring technique in the LiDAR principle. And there are some different types of LiDARs. I list here are all SICK lasers. So there are some popular laser brands you may know. So one is SICK, the other is Hokuyo from Japan. And for 3D LiDARs, the Lidar is the most famous one. Lidar, they have like 16 lines, 32 lines, 64 lines, 3D LiDAR. And also there's another cheaper option of the 3D LiDAR. Is called RoboSense. RoboSense is it's a Chinese company, and they can build the LiDAR like similar to what they have from Lidar. All right, so that brand makes the Lidar price dropped a lot. All right, so those are some of the brands that you can famous brands that you can use in if in the future you want to buy some laser scanner or lidars. All right, so the 2D lidar, so the 2D SICK laser, it can provide the measurement range of 80 meters and with a bearing angle 180 degrees, and for each 0.5 degree it has a hit. It has a reading, right? And there are also some 360 degrees lidar or lasers or laser scanners, so they can scan 360 degrees. And then for 3D lidars, they can provide longer range because they more or less they're using it outdoor, and they can range from 120 to 350 meters. And bearing is they will always have the 360 degrees for the horizontal, and for vertical is not that much on the field of view. All right, so the model of the error on the 2D laser sensor or LiDAR sensor, they are different from what we have in Sonar. So the laser will always provide you the accurate range and accurate bearing readings. So which means from the reading you will have multiple range, which is R, and multiple bearing angles, which is theta, for each of the reading. And then you can use the range and bearing to recover the XY location of that point. All right, so which means if you have a range and bearing from the reading of the 2D laser, then it's quite easy to recover the XY from it. I think if you've tested, you do some practice on that already. All right, so another technique is about if you use a 2D laser in the indoor environment, then you may have some readings on the wall, and the wall is a line. The wall is a line, and you need to detect the line. You need to detect the line from the laser. All right. So what we can do is we can detect the line something like this. So first, you need to know what's the equation of line, right? Suppose we have a point on the line, which is xy, and we have two endpoints, which is x1, y1, x2, y2. And the tangent of this segment can be calculated by y minus y1, x minus x1, divided by x minus x1. And the tangent of this segment can be calculated by y2 minus I1 and x2 minus x1. And then the tangent of the two segments are the same. Then we can get the line equation. And we can rewrite the line equation by y equal to mx plus c, or y minus mx minus c is equal to 0. And if you have multiple points, you can fit the line by minimize this error. So suppose all the points are on the same line, then if you put the xy of each point into this equation, it will be near 0 or equal to 0. And then you use all of the points together to make a linearly square. Then you can fit your m and c out. That is your line equation, right? But for most of the cases, you will get the readings from the laser, something like that, right? And which means you need to detect which line segment it is, right? So here's the technique. So first, suppose you have those kind of readings from the scanner. Then you first use all the points to fit that line. You use all the points to fit that line, and that line is definitely not the accurate line, right? But don't worry. After you fit that line, you can calculate all the distance from each of the points to that line, to that fitted line, right? And then you find the largest distance. You may think that point is definitely not from the same line. And what you need to do is you split the data from that point with the largest distance. Then you fit two lines. And you can see the points on the left, they are more or less the same line, right, with relatively small distance. And if you find the points on the right, they still have large distance from point to the fitted line. And you calculate those distance again, and you find the largest point. So largest distance, you find the point with largest distance. And then you split those points from that point. And then you fitted two lines, and you can see the three lines you fitted they are more or less the correct one. Right, so this is about the technique about how to fit the line from the laser data. All right. So there are some applications. So most of the application is about mapping and area monitoring and localization, and they also use it for object detection as well. And the most commonly used application at the moment for the 3D LiDAR, is the autonomous driving. So for every single project about autonomous driving, they are using 3D LiDAR. And here is a video. Here is the video about the data it gets from the autonomous driving. It's a 3D LiDAR. As you can see there are multiple lines. The multiple lines means they are multiple lines on a vertical direction. So that makes it 3D. And also you can see the observation, so the scanning angle is 360. It's 360 on the angle and multiple lines on the vertical direction. And they use it on the autonomous driving. And you can see from the laser scan, you can nearly see everything in the shape, in the geometry point of view. You can nearly see everything surrounding the car, and which include a lot of information which can be used in autonomous driving. All right, so this is nearly all. This is nearly all for today's lecture, and then let's move to the hands-on activities with Malin. All right, thank you very much. So if you have any questions about the project, or if you have any questions about the triangulation of stereo camera, please just let me know. All right, thank you very much. Let's